What specific problem does your paper address regarding the divide between open source and closed source large language models, LLMs, and why is this issue particularly relevant in the current landscape of AI development?
My paper addresses the critical issue of the divide between open source and closed source large language models, LLMs, focusing on the implications of transparency, accessibility, and equitable distribution of AI benefits. This issue is particularly relevant in the current AI landscape as closed source models, like GPT-4, dominate performance benchmarks due to their proprietary datasets and significant computational investments, which raises concerns about reproducibility and the concentration of resources within a few organizations. In contrast, open-source models such as Llama and Bloom promote accessibility and community-driven innovation, enabling researchers to advance natural language processing without extensive resources. The paper highlights how this divide exacerbates inequities in global AI development and restricts many practitioners from effectively competing or building upon existing systems. By exploring these dynamics, the paper underscores the urgent need for a balanced approach that fosters innovation while ensuring ethical considerations and equitable access to AI technologies.
Can you explain in detail how your proposed innovations like low-rank adaptation and conditioned reinforcement learning fine-tuning work within the context of open-source models? Please illustrate it step by step.
Low-rank adaptation, LoRa, and conditioned reinforcement learning fine-tuning, CRLFT, are innovative techniques that enhance the performance of open-source large language models, LLMs, while minimizing computational costs. LoRa operates by freezing most of the model's parameters and optimizing a low-rank adaptation of the model weights, which allows for efficient fine-tuning tailored to specific tasks without the need for extensive computational resources. This method has proven effective in maintaining high accuracy, particularly in domain-specific applications, as evidenced by its competitive results on benchmarks like GSM-8K. On the other hand, CRLFT employs reinforcement learning principles to fine-tune models based on specific conditions or objectives, enabling them to adapt more effectively to particular tasks or datasets. This approach allows models to learn from feedback in a structured manner, improving their performance in targeted applications. Together, these techniques exemplify how open-source models can achieve significant advancements in performance and accessibility, enabling researchers and developers to leverage advanced NLP capabilities, even in resource-constrained environments.
Could you provide a simple example that demonstrates how one of the techniques you've discussed, such as LoRa, is applied to a practical NLP task? What steps would you take to implement this method?
One practical example of applying low-rank adaptation, LoRa, in an NLP task is in fine-tuning a model like GPT-3 for textual summarization. To implement this method, the first step would involve freezing most of the model's parameters to maintain the pre-trained knowledge, while allowing only a small subset of parameters to be optimized. Next, you would create a low-rank adaptation of the model weights, which reduces the computational costs associated with fine-tuning. After setting up the model, you would prepare a dataset of documents and their corresponding summaries to train the model on this specific task. Finally, you would evaluate the model's performance on a benchmark dataset, such as those used in summarization tasks, to ensure that it achieves competitive results while utilizing significantly fewer resources than traditional fine-tuning methods. This approach exemplifies how LoRa enhances accessibility and efficiency in NLP applications.
What are the main advantages of using open-source LLMs as you argue in your paper? How do these benefits manifest in terms of accessibility and performance compared to closed-source models?
The main advantages of using open-source LLMs, as argued in the paper, include enhanced accessibility and competitive performance. Open-source models like Llama and Bloom democratize access to advanced NLP technologies by enabling researchers to run tasks on single GPUs, significantly lowering computational barriers while maintaining high benchmark performance. Techniques such as low-rank adaptation, LoRa further enhance this accessibility by allowing fine-tuning with reduced resource demands, making it feasible for smaller organizations to utilize these models effectively. In terms of performance, while closed-source models like GPT-4 excel in generalization due to proprietary datasets, open-source models have made significant strides in narrowing the performance gap through innovative optimization strategies, achieving competitive results in specialized applications. This combination of accessibility and performance not only empowers a broader range of users, but also fosters collaborative development, ultimately contributing to a more equitable distribution of AI benefits.
How did you validate the comparative performance of open source versus closed source LLMs in your study? What specific datasets and metrics were utilized for this evaluation, and what were the key findings?
In my study, the comparative performance of open source versus closed source LLMs was validated through an evaluation of state-of-the-art benchmarks such as HumanEval and GSM-8K. Closed-source models like GPT-4 were found to dominate these benchmarks due to their access to proprietary datasets and extensive pre-training corpora, which span hundreds of terabytes. Key findings indicated that while closed-source models excelled in generative tasks and multi-step reasoning, open-source models have made significant strides in closing the performance gap through techniques like low-rank adaptation, LoRa, and conditioned reinforcement learning fine-tuning, CRLFT. For instance, models like NVIDIA's NVLM-1, 0D72B demonstrated domain-specific excellence, achieving notable improvements in mathematical reasoning and coding tasks. Overall, the study highlighted that while closed-source models lead in performance, open-source models are increasingly competitive, particularly in specialized applications, emphasizing the importance of accessibility and collaborative development.
What limitations did you discover concerning open-source LLMs? Are there specific scenarios or applications where these models might struggle compared to their closed-source counterparts?
Open-source LLMs face several limitations, particularly in performance and resource availability. While they have made significant strides in narrowing the performance gap with closed-source models, they often lag behind in absolute performance due to their reliance on narrower dataset scopes and fewer computational resources. For instance, closed-source models like GPT-4 excel in generative tasks and multi-step reasoning, leveraging proprietary datasets and extensive pre-training, which open-source models struggle to match. Additionally, open-source models may encounter challenges in specialized applications where domain-specific expertise is crucial, as seen with models like Clinical BERT and Legal BERT, which outperform general-purpose models in their respective fields. Furthermore, the benchmarking potential of open-source models is limited by their need for collaborative resource pooling and parameter-efficient strategies, which can hinder their adaptability in high-stakes scenarios requiring robust performance.